Thank you all for attending. In this Berggruen Forum, I'd like to describe the impetus for and the creation of the so-called Alfred University Calculus Initiative. This work is partially funded by a grant from the National Science Foundation. In this talk, I will briefly answer the question, what is calculus? And, operative word is briefly. Provide motivation and rationale for creating a new calculus course. Describe changes in pedagogy in the late 20th century. And summarize recent changes in our own calculus course here at Alfred. I will give a brief overview of the National Science Foundation's TWOS program, through which the Alfred University Calculus Initiative is funded, and then discuss the initiative itself. I will review our methods of data collection and analysis, and conclude with a summary of the work yet to be completed. Am I screaming? I feel like okay. Okay. So, what is calculus? Well, the word calculus is Latin for stone. This may be why people think calculus is so hard. Yeah. Here's a photograph from one of my recent classes. I have students call me Professor Herman. Shall I wait? Calculus was formally developed in the 17th century by Isaac Newton and Gottfried Leibniz. Besides making many calculus students miserable, calculus is also responsible for the most notorious scientific feuds of all time. The story goes something like this. Newton developed his ideas between 1664 and 1666 and summarized them in an unpublished paper. Leibniz independently developed his own ideas by 1675. He knew that Newton had new methods, but he did not have direct access to his mathematics. A formal correspondence began in 1676 through an intermediary, and the two amicably shared a few discoveries. Leibniz eventually published the first paper on calculus in 1684. It included no mention of Sir Isaac, thus a bitter clash began. Thanks to both men, our world was forever changed by calculus. After all, it is used in every branch of the physical sciences, engineering, economics, business, actuarial science, computer science, statistics, and in other fields. Calculus is the study of two types of change. A rate of change measures how quickly one quantity is increasing or decreasing with respect to another. For instance, suppose a ball is tossed straight up into the air. Calculus can be used to find the ball's velocity at a given time and its maximum height. In fact, calculus can be used to describe the rate of increase or decrease of, and to optimize, any well-behaved quantity, such as height, area, cost, and profit. Geometrically, the ball's velocity at a given moment in time is equal to the steepness of the height graph at that time. The accumulated change is the net or total accumulation of all intermediate changes in a quantity. You never thought you'd be coming to a calculus class today, huh? For instance, suppose a ball is tossed straight up in the air. It necessarily travels at varying velocities. Calculus can be used to determine the net change in the ball's height over a given time period. In general, given the rate of change of any well-behaved quantity, such as position, temperature, population, or profit, calculus can be used to find the net change. Geometrically, the net change in the ball's height over a given time period is the net area bounded by the velocity graph. According to the late 19th century mathematician W.B. Smith, quote, "Calculus is the most powerful weapon of thought yet devised by the wit of man," end quote. But this statement alone will not convince a typical first-year student that calculus is useful and easy to understand. In fact, many traditional norms and modern trends have undermined the ability of teachers to successfully create positive and productive learning experiences. Probably the most common impediment is trouble with pre-calculus. Many first-year students do not have sufficient skills, but unfortunately, a remedial pre-calculus course can be ineffective and downright discouraging. especially if the content is presented out of context. The reality is that students in the same classroom have varying backgrounds, interests, and abilities. If not handled correctly, the stronger students excel, while the weaker ones fall behind. Standard deviations are typically quite high. Students tend to bring in some amount of emotional baggage. For instance, they are conditioned to think that calculus is difficult and abstract. Although some calculus teachers do a great job incorporating real applications and active learning experience into their courses, a traditional calculus course may lack meaning, context, and a chance for individual discovery. Without appropriate context, the content is unmotivated, and without a chance for discovery, the purpose of learning calculus is ambiguous. I am a teacher of calculus, and by no means am I innocent of any wrongdoing. Yes, guilty. I, along with countless others, have been guilty of a few false assumptions. Students remember what they learn in pre-calculus. False. Calculus is or should be the weed-out course for science, technology, engineering, and math majors. This is false. A 30 to 40% failure rate in calculus is normal, hence acceptable. This is false. And calculus is as interesting to students as it is to teachers. This is clearly false. During a time when the United States typically ranks between 25th and 30th in the world in performance on standardized tests in mathematics and science, the worst-case scenario is that a negative experience in first semester calculus course may discourage an otherwise exceptional student from choosing a career in a STEM discipline. A renewed focus on the teaching of calculus and other STEM courses dominated the latter third of the 20th century. One of the most comprehensive and long-term studies took place at Purdue between 1966 and 1993. The study found that 43% of engineering students eventually left engineering because of difficulty with calculus, chemistry, or physics. The predictor for the success in the engineering program, however, was not SAT score, but first semester GPA. In fact, the study showed that a student earning an A in first semester pre-calculus had about the same retention rate as a student earning a B in first semester calculus. Based on SAT scores, this pre-calculus student, on average, would have failed first semester calculus, earned a lower first semester GPA, and eventually dropped out of the program. The researchers concluded that students should take courses during the first semester that will enable them to do their best. In 1986, with funding by the Sloan Foundation, Ronald Douglas organized and held a conference at Tulane University that focused on reforming calculus. The content centered on applications and student understanding. Pedagogy focused on cooperative learning and writing projects, and the use of technology enhanced learning and aided in visualization. The C4L program, or Calculus, Concepts, Computers, and Cooperative Learning at Purdue University, and CCH, or the Calculus Consortium at Harvard, were two of the most popular flavors of reformed calculus. The reasons for the movement were obvious. Failure rates in calculus were as high as 40%. Instruction featured rote learning without understanding, and students were bored and unengaged. Advocates for the program hailed its emphasis on thinking, not just on memorizing, and its development of a deeper understanding of calculus concepts. Opponents, on the other hand, complained that students do not learn to work with difficult calculations, and they become dependent on technology. The movement ultimately created two factions whose fierce battles rivaled that of Newton and Leibniz. In the end, the calculus reform movement lasted 10 years or so in its complete form, although the individual components are often used today. Of course, no conversation about 20th century higher education would be complete without some mention of the clientele. Generation Y, or the millennial generation, consists of individuals born between 1980 and 2000, give or take. Much is known about this cohort, and this information can help guide educators in making decisions about how to teach these students. Here is a list of some suggested teaching tips. As we will discuss shortly, the Alfred University Calculus Initiative has been created with each of these tips in mind. Develop opportunities for experiential learning. Provide hands-on activities in the classroom. Satisfy the need for social interaction. Encourage students to exchange information verbally. Cover less and have students cover more. Create an environment that provides positive reinforcement. Organize class activities around a 20-minute attention span. And tie learning to real-world problems. From this list, one may get a clear picture of what a 21st century educational environment could look like. In order to create such an environment, educators must incorporate modern methods, techniques, and materials into the classroom and curriculum. Fortunately, much evidence exists for the effectiveness of many current trends in STEM education. For instance, there exist countless studies and projects on flipped and blended classrooms, active and cooperative learning, video lectures, lessons, reviews, and examples, digital textbooks, online modules and applets, and online homework, testing, and assessment systems. Now that we have some historical, pedagogical, and societal perspective, let us examine how Alfred University fits into this story. In 2004, the Division of Mathematics switched from reformed calculus back to the traditional calculus model. This was a year before I arrived. Thank you. In 2007, the so-called Common Ground meetings, led by Dr. Wong, brought together engineering, science, and math faculty members. The meetings promoted discussion, but did not generate much action. In 2009, what I call the FIEMs, or First Year Engineering, Math, and Science meetings, led by me and Alan Meyer, focused on identifying common threads through first-year STEM courses. These meetings led to the creation of a preparation for calculus, which was a packet of lecture notes first used in the fall 2009 Calculus 1 sections. The intention of the notes was to review necessary pre-calculus topics in the context of science and engineering, and to create a level playing field for all students. While the notes prepared the students well, they required at least 3 weeks of the semester to cover. Instructors were forced to eliminate some content from the curriculum and postpone other content to Calculus 2. Additional FIEMs meetings led to the offering of problem solving in the physical science, which was a B-block course team taught by me and Dr. Toot. It covered basic calculus concepts in the context of physical applications, and it was meant to remediate struggling calculus students. While students provided positive feedback about the experience, the course did not seem to help them get back on track. With more and more frequency, my mathematics colleague Dr. Cook and I would come to the mutual conclusion that maybe the calculus curriculum itself was the problem. At the end of 2010, we began seriously discussing changes in the first semester calculus curriculum and delivery method. We realized that we can teach old dogs new tricks, even if they have only a basic foundation. At about the same time, Dr. Cook and I were working through the details. I came across the solicitation of the National Science Foundation's TWOS program, or Transforming Undergraduate Education in STEM. This program supports efforts that bring advances in STEM disciplinary knowledge into the undergraduate experience. It supports the creation and adaptation of STEM learning materials and teaching strategies. It supports projects that enhance our understanding of how students learn and how faculty members adopt instructional approaches. And it supports projects that have the potential to transform the conduct of undergraduate STEM education. During the first few months of 2011, I researched and wrote a proposal for the so-called Alfred University Calculus Initiative and submitted the proposal in May of 2011. The grant was awarded in May of 2012. The project abstract submitted with the proposal has been crafted to embody the motivation and rationale for the project, as well as to emphasize its focus on 21st century pedagogy. Here are a few excerpts. The Alfred University Calculus Initiative, also called AUCI, is a multifaceted project designed to meet many of the challenges facing STEM teachers in today's classrooms. The overall goal of the AUCI is to increase understanding and success in calculus and pre-calculus, while maintaining the level of rigor and breadth required for post-calculus courses. The AUCI seeks to achieve its overall goal and related objectives by combining a new curriculum, classroom transformation, video lessons and examples, online quizzes and homework, and web-based implementation. This project is being informed by current research and trends in STEM education, which include engaging students with visual and online technology, creating an active learning environment in the classroom, and incorporating meaningful applications. Let's look more closely at the 7 components of the AUCI. At the heart of the project is the new curriculum, which has been realized in textbook form thanks to a recent sabbatical. The 8 chapters focus on function type. The content exploits the interplay between calculus and pre-calculus, and the presentation continually reinforces the main ideas. The text contains 42 sets of lessons and examples, all of which have been recorded to video. Lesson videos, which average less than 6 minutes in length, contain short bursts of information, and examples videos, which average 10.5 minutes in length, demonstrate standard problems and solutions. In order for a student to assess his or her understanding of the lesson, we have created a corresponding quiz that the student completes through a homework system called WebWork. A nice feature of WebWork is that it provides immediate feedback. The textbook also contains activities that correspond to the lessons. Activities are completed in class while the instructor employs active learning techniques. Post-lesson reinforcement, practice, and drill occur during the follow-up homework assignment, which is also completed through WebWork. All course information is accessible through the AUCI website, which can also be used to support off-site use. One of our goals is to partner with GST BOCES and offer this course to high school students for college credit. The course materials will be accessed online, and the class meetings will be run by the high school teachers from their own campuses. The best way to describe how the AUCI works in practice is to list the sequence of steps that a student must follow to successfully complete a lesson. Let's begin with a Monday assignment. Step 1. Watch the lesson video while following along with the text and taking notes. Record questions that arise. Step 2. Watch the examples video while following along with the text and taking notes. Record questions that arise. Step 3. Complete the WebWork quiz, which closes at 11:59 p.m. Note that the first 3 steps are equivalent to assigning a reading from the textbook along with a few simple practice problems. This process ensures that the student is prepared for the class activity the next day. Step 4. On Tuesday, the student attends class prepared to work, talk, and ask and answer questions. During the class meeting, the instructor summarizes the lesson, the instructor answers lesson and homework questions, and the student completes the activity included in the textbook. During this time, students work in groups while the instructor implements active learning techniques. Step 5. By Wednesday night, the student must complete the WebWork homework, which closes at 11:59 p.m. The process then repeats for the next lesson. One of the most important questions, of course, is how effective is the project? We hope to answer this question through data collection and analysis of treatment and control groups, final exam scores and course grades, surveys and interviews, and even test scores from Calculus 2. So far, we have collected a substantial amount of data, which is exciting, but sometimes it gets a little overwhelming. Recently, we piloted only the curriculum, and the raw data suggests that it is highly effective on its own. The treatment group consisted of 58 students, split over 2 sections. Each instructor delivered lectures from the new AUCI textbook. The control group consisted of 59 students, split over 2 sections. Each instructor delivered lectures from a traditional calculus textbook. A common final exam, based on the traditional curriculum, was administered to all students. The average final exam score for the treatment group was 80.1%, a B-, while the average for the control group was 65.3%, a D. This is a 15 percentage point improvement. Furthermore, the drop in the standard deviation by 7 points suggests that the AUCI curriculum kept more students closer to the mean. We tracked the 2 groups through Calculus 2 and found that the treatment group scored almost 10 percentage points higher than the control on the first test. The standard deviation of 11.8 for this test shows that 68% of the students in the treatment group earned a C or higher, and 95% of them passed the first test. Keep in mind that these are only raw numbers, and they have not been adjusted to account for other potential factors. We recently completed the first full pilot, which included the curriculum, videos, activities, and online quizzes and homework. Although the average final exam score was not as high as the curriculum pilot, it was still 10 percentage points higher than the control, the difference of a full letter grade. An in-depth look at survey data is pending, and hopefully we will find some information there that will guide us as we move forward. But regardless of the solicited questions, I can reasonably make some valuable observations since I stand before these students 4 days a week. Teaching methods such as video, web work, active learning are new and uncomfortable to many students. They must quickly adjust to these methods. Students not only must remember to utilize familiar study techniques, but they also must develop new study habits that match the process and methods. For instance, students are not always willing to take notes while watching a video as they would for a live lecture. Active learning is active, much to the disappointment of the classroom daydreamers, texters, and nappers. Some students just don't seem to want to talk about rates of change at 8:30 in the morning. Some students mistakenly perceive the AUCI as an online course without realizing that one of the most important components is the in-class activity and discussion. Since it is no secret that the AUCI is a new project, some students tend to blame it rather than the course content or their own study habits during times of trouble. We're only in the 9th month of a 2-year project, so there is still much we need to accomplish. Here is a brief list of work to be completed. Run a treatment versus control for the video lessons and examples. Compile and analyze recently gathered data and compare with previously analyzed data. Collaborate with BOCES and prepare to offer the AUCI to area high school students. Organize a late summer workshop for high school teachers. Write and submit annual reports to the NSF, and write and submit research articles. Lastly, I must give credit where it is due. Darwin Cook is responsible for all things web work and contributed substantially to the reorganization of the course content. And Addison Fry has single-handedly created and continues to maintain the AUCI website. Please visit it if you get a chance. Finally, Danielle Gagne and David Terry make up our fine evaluation team, and I'll bet they both wish I would stop filling their inboxes with questions and demands. Please contact me directly if you have any comments or questions that have not been answered here, and thank you for listening.